So 2.5, we're talking about transformations. We're going to talk about both rigid and non-rigid transformations. A rigid transformation would be like me walking across the room, right? My shape's not changing. I hope I might be getting fatter, but that's rigid. A non-rigid would be grabbing a gummy bear and squishing it, right? That gummy bear became wider, right? So that's rigid and non-rigid. We're going to do vertical, horizontal shifts. We're going to do reflections. We're going to actually talk about reflecting across the x-axis and the y-axis. And then, of course, the non-rigid transformation, which is stretching and compressing. So many transformations, we're going to start with the parent function. In this case, we're looking at the graph of starting with y equals x squared. And then comparing that with the graph of y equals x squared plus 2. So what did that plus 2 do? Okay. So we added 2 to the function. We added 2 to the output of the parent function. We added 2 to the value of f of x. That makes sense? Okay. We're not changing the x value. We're changing the y value. And that's why adding 2 is a shift up 2 units. So far, so good? Yeah. Oh, well. So this is what I was just talking about. In the case of this problem, our f of x is x squared. And so we took the function, added 2 to it, shifted it up 2 units. What if we put the 2 instead inside with the x value? We're now not modifying the value of the function. We're modifying the value of the input. We're modifying the value of the x value. Okay. When the x value changes, we're changing along the x-axis. That's why it's a horizontal shift. So x minus 2 causes what kind of a shift? To the right 2. So, and as I've said this way many times before, if it's inside a grouping symbol, it's going to be backwards from the obvious. Okay. And we're going to see that with horizontal. Have we done horizontal compressions? Or have we stuck with vertical? We stuck with vertical, didn't we? Yeah. Okay. So again, when we have the function x minus 2 squared, we're saying f of x minus 2. So saying it is that f of x minus 2, again, it's simply saying we are changing the x value. We're changing this graph horizontally. So writing all of these out, f of x plus c, c units up. F of x minus c, c units down. F of x minus c is c units to the right, and f of x plus c is c units to the left. And as we've done in the past, we can do horizontal and vertical shifts at the same time, right? I can take my hand from here, move it down and to the right. My hand didn't change sides. That was a rigid shift, right? Okay. We're going to graph a couple. We're going to sketch these. This is going to be rough sketches here. I want to sketch g of x, which is x cubed plus 1, minus 1. What does that look like? Does that make sense, what he just said? So if I had like a parabola like this, if I leave this side alone, but take this side over here and bring it down here. That's what he said, right? What did I just graph? Okay, this is f of x equals x cubed, right? You're going to continue to argue till we get it right? Huh? Down one? Something like this? Okay. Is everybody agreed? 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 You agree? Left 2, up 1. So this point here is going to be about there. Maybe something like this. Not to scale. Okay. The next 2 screens have the nice drawings. Get off the ugliest color in the world pen. So there is the x squared plus 1. Let me go back real quick. I know, I'm going back. There's the first one. They just talked about it over here. So there's the first graph. Next slide. And there's the second one. So it doesn't matter if you do the vertical shift first or the horizontal shift first. It doesn't matter at all, right? If you move it, you move it. Horizontal first, vertical shift, doesn't matter. Okay. Go. Reflections. To have a reflection, A is going to be negative. If you see A is negative, it reflects. So here you have 2 graphs. You have the graph of h of x, which is negative x squared, the dark one down below, and f of x, the parent function, up above, a little bit lighter. It's just a mirror image. To reflect across the x-axis, we are changing the y value. That makes sense, doesn't it? If you're changing the y value, you're going to reflect across the x-axis. To reflect across the y-axis, we're going to change the x value. So notice where the negative sign's at. Pay attention to your domain. The domain of g of x. If I have negative square root of x, x has to be non-negative, right? You can't take the square root of a negative number. So make sure your domain is correct. But look at this one. If h of x is equal to the square root of negative x, now x has to be non-positive. Do you see why? If x is a negative number, I have negative 6, which would be positive 6, right? Negative 4, right? And on the last one, if I'm taking the negative square root of x plus 2, I know that x has to be greater than or equal to negative 2. Where did that come from? Where did this come from? Well, I'm asking. How do you know that x has to be greater than or equal to negative 2, Caddy?
Well, if it's like negative 3 plus 2, you'll get that negative 1 and 2.
Okay. Sure, but where did we come up with this whole concept of x is greater than or equal to negative 2?
Oh.
I'm on the bottom one. I've talked about this before when trying to determine the domain of a function. There are two problems, two issues with domains. One of them is you can't divide by, and the other one is you cannot take the square root of a negative number. So how do I guarantee that this is non-negative? Non-negative, right? To solve this, I would subtract 2 from both sides. That's where this comes from. Subtract 2 from both sides, x greater than or equal to -2. Right? Okay. F of x equals x to the 4th. That's what it looks like. Did you already know that? Is that not the same thing as x squared? It's flatter at the bottom. Okay. It's still curving continuously. Why does it appear to be flatter at the bottom? No, there's no compression here. Because it's also a lot steeper. Okay, let me ask you this. I've got a straight line with a slope that's not 0. How many times will this line touch the x-axis? Once. And what does it do? Goes right through it. X squared. How many solutions does a quadratic have? 2. How many solutions does a quartic have? 4. So if you think about it, if this is what 4 solutions might look like, well, in this case, it's only 1 solution that's repeated 4 times. Okay, so it's a quadruple root. That's why it appears to be flatter. Okay, but who cares? That's what the function looks like. Okay. I want an equation for letter A. What's the equation of that? Why are you saying negative? Okay, you see a reflection, so it's opening down. Negative x to the 4th. Okay, is that it? Why? Perfect. So I don't care what the function is. And here in a little bit, we're actually going to see a graph of a function we don't even have an equation of. We can still do transformations on that graph. Okay. Number 2, or number B.
Negative x to the 4th.
That's to the 4th. Okay. Because we're changing the value of x. That's what's causing the shift to the right. How are we doing? Are we kind of quiet and deadish today? Huh? Gloomy. This is just the answer to what we just did. Non-rigid transformations. So a while ago, we were talking about horizontal and vertical shifts. Now we're going to talk about compressions. Non-rigid, it's transformation that causes a distortion. We're going to change the shape of the graph. To change the shape of the graph, there's 2 ways to do it. You can either multiply the entire function by some value, or you can multiply your x by some value. If you're multiplying the function by a value, it's a vertical change. Okay. If the number is greater than 1, it's going to be a vertical stretch. If it's between 0 and 1, it's going to be a vertical compression or vertical shrink. If we're changing the value of x, it's horizontal. And it's kind of opposite of what I just said. If it's greater than 1, it's going to be a horizontal shrink. If it's less than 1, it's going to be a horizontal stretch. Okay. Think of it as it's inside a grouping symbol, so it's going to be backwards from the opposite. Just like when you subtracted on the inside, it moved it to the right, right? So same concept, backwards from what you would think. H of x is equal to 3 absolute value of x. What does that graph look like? A steep V. Why is it steep? And what's that 3 do to it? Okay, this 3 is a vertical stretch, so it stretches it out, makes it steeper instead of down here. It's up here. Okay. How about B? Okay. Okay. Yeah. Less than 1, it's going to be a horizontal. So here's the first one. It's a horizontal stretch because we're multiplying the function by 3. I'm going to scroll down. Put this out of the way. There's your 1/3. Because we're multiplying the function by 1/3, it's a vertical compression. They like to use the word vertical shrink here. Yeah. Here's a graph. We're just going to talk through this one, okay? I don't know what this equation is, but it's a graph. Look at part A. Part A says, okay, let's take that graph above, but we're now going to change it to f of x minus 5. What is the graph going to do with f of x minus 5? Right 5, okay? Part B, we have negative f of x plus 4. Reflected which way?
Down.
Across the x-axis. And up 4. Part C. Which way? Compressed which way? Horizontally or vertically? It's vertical. It's compressing it this way. Okay. Okay. We're changing the value of the function. We're changing the y value. We're changing f of x. We're changing it this way. Okay. So that's a vertical compression. It's that gummy bear. I'm smashing the gummy bear. It's now 1/2 as tall as it was, which made him fatter. Okay. Part D. What's going on with part D? Reflected across the x-axis because we changed the sign on the y value. What else?
Wait, no, move to the left.
Left 1. It's inside, so think backwards. Part E. No, sir. So it's reflected across the y-axis because the x value is being changed. Now let me ask you this. Look at the graph they gave us. If I reflected that graph across the y-axis, what would it look like? Exactly the same. Why? This graph is symmetric about the y-axis. So if something's reflected across the y-axis and it's symmetric across the y-axis, you will see no difference. Okay. Letter F, what's going to happen? Take that whole graph, that whole wave, move it down 9 units. And part G, what's going to happen? On G, there's no reflection. On G. Okay, it's inside the parentheses. What is it modifying? Is it modifying the function or is it modifying the x? Okay, because it's modifying the x, it's going to affect horizontal, right? Okay, so it's a horizontal what? Nope. You would think it is, but because it's inside, it's a horizontal stretch by a factor of 3. That's exactly right. It stretches it by a factor of 3 in the horizontal direction. Okay. What's that? Okay. The 1/3 is inside the parentheses. It's modifying the x, which is the horizontal direction. Because it's inside, it's going to be backwards from the obvious. 1/3 is actually going to be a stretch. And stretching something by a factor of 1/3 makes no sense. So take the reciprocal of that. We are stretching it horizontally by a factor of 3. And part 2, number 2, use the graph of f of x equals x cubed. I want the equation for the graph that you see on the screen. Everybody, write it down. Write down the equation of the graph you see on the screen on number 2.
Yeah, what is the number?
Just, if you can't see it, make something that makes sense.
Okay.
The squares are counting by 1. It's hard to see the squares. One, 2, 3, 4, 5, 6. 1, 1, 2. Does that help?
Yeah.
4, 5. Do y'all care about the other directions, or are we okay just with those? The equation of number 2. You're looking at the graph. I want you to write down the equation. Type it in your calculator, it's fine. I think you're right the first time, aren't you? You're good. You're good. Where's yours? You're missing one thing, and there should not be an F on there. There should not be an F. Oh. I know what you did. Okay, now write it in terms of x cubed. You're exactly right with what you did, but I want to see the x's in there. I want to see the exponents in there. Okay. Okay, and have an idea what you're thinking, but I want it to look like x cubed. I don't want it to look like f of x. I want it to actually look like x cubed. But shouldn't that be over here on the outside? Yeah. This is what you had, right? Mm-hmm. It is. Yeah. What you got? Nothing. Okay. So seeing some good stuff on there. Let's talk through this real quick. I know that this graph kind of looks like this, right? This is what f of x is. So comparing my graph to their graph, what do you see that has taken place? There's a reflection going on, right? Now these are kind of odd here. It's an odd function, but anyway, because it's an odd function, I can see a person saying, well, it was flipped this way. It is, but I can also see a person saying it's flipped this way. Can you see both? Because it's an odd function. Think about it. For a function to be odd, this point is say -3, -3. This point over here is +3, +3, right? It's reflected through the origin, which means both signs changed. So in my mind, I could reflect it across the y-axis, or I could reflect it across the x-axis. It doesn't matter to me right offhand. It's a reflection. Okay? It's a reflection. What else is happening? So we know there's a reflection going on. So we have a reflection. What else we have going on? Okay. Yeah, let's pay attention to this point here. That point transferred from there to here. Down 3, left 2. Now, if you chose numbers different than that based on how you see the graph, the distance, I don't care. I saw some 3.5s. I don't care. I don't care. Okay. So how do we do that? We're going to call this one g of x, I guess. It's something cubed. There's got to be a negative somewhere. There's got to be an x somewhere. Okay. Okay. Where's this 2 go? And it's going to look like? Okay. So I know I have an x plus 2. What's this going to look like? I'm moving the whole function down. Okay. The question is, does the minus go there or does it go there? Okay. And I will tell you that putting it in one place versus the other is actually 2 different graphs. Okay, this one is going to be on the outside. That graph is going to be over here. Change the one graph. Do you still have them in your calculator? Not Parker, change on the one that I did, change that to a minus. The one that has the negative x, change it to -x minus 2. And look at that one. Just to mess you up even more. Did it lay right on top of my answer? Yeah. Okay. When you start jacking around with transformations and reflections, it messes all kinds of things up. So you can get So what we just have is another answer for this question that worked. If you graph those, it's the same graph. It's just a matter of how you're counting the reflection. Okay. Chances are this problem here, this is the answer. I don't know. Hopefully they'll accept both on the homework. What's going on with number 3? What's the equation of that graph? Absolute value. It's moved which way? And down and right. No reflections? Okay. So down 6, minus 6 on the outside.
-2 on the
Right 2, minus 2 on the inside. All right, guys. And that wraps up 2-5.